Hello everybody, I'm Thomas Schütte from PLASUS. PLASUS is a German company who is specialized in developing and manufacturing plasma monitoring and process control systems since 25 years now. Today I wanted to address the topic of active process control in production lines, whether and how it is used today, and what are the objectives for the future. Since HIPIMS is still a cutting-edge technology in production lines, I will demonstrate the benefits and perspective of active process control at a HIPIMS application. So far, quality control is mainly done at the final product. Whether it's a batch-to-batch application or an inline application, the final product is evaluated and then the process is adjusted. However, there is no data taken from the real plasma process itself. And with this, you are missing a lot of opportunities to control and to monitor your process in situ and in real time. On the other side, there are a lot of metrology tools available today which can do this job. They can measure plasma parameter in situ and in real time. They are capable of controlling specific parameters, reliable and on a long-term basis, and they are ready for system control. And again, for all future applications, there is still the need of enhanced process stability to making the product better, to making the process more stable, to increase production yields. And in our opinion, this can only be achieved with smart and reliable sensor technology, which will then provide data for a comprehensive data treatment within the framework of Industry 4.0 and IoT, and as input for artificial intelligence evaluation. Here I have listed a selection of sensor technology which are available today. I don't want to go through this in detail. I just wanted to show here there are a lot of different types of sensor technologies available which can be adapted in production line and which can be used. So whatever you need, pick the one you need and make use of it in your application, in your production line. But this is only one part of the game. What the sensor technology do is giving inside parameters here of the process, and the idea of Industry 4.0 and IoT is actually to linking even more parameters. So the final goal would be to link parameters from the system itself and also from the final product and from the process, from the plasma process, and linking them all together in one database. And only with this you can evaluate the data as a complete set of data and then make your process more stable during the next run and give a better and faster quality control. And this I want to show you in one part for the sensor technology at a reactive HIPIMS process. Now, in a HIPIMS process, you all know we have two parameters we wanted to change, especially in a reactive HIPIMS process. On one side, we have the ion density, which is one feature actually of the HIPIMS processes, and you can adjust the ion density or the ionization degree by the peak current of the pulse. This is okay and known for the metallic mode, but now if you go for the reactive mode, the peak current will also change if you add the reactive gas. So you have two parameters, the reactive gas on one side and the ion density or peak current on the other side you want to control, but they are dependent on each other. So the idea is now to make a combined to combine different sensor technology and to measure both both parameters independently. And this actually what we did with our colleagues from the Fraunhofer IST in Braunschweig. So what you see here, we had the sputtering application with dual cathode arrangement. And what we did is we looked with the spectroscopic monitoring system from the top to the bottom of each cathode and took the spectrum while the process was running. At the same time, we acquired also the pulse voltage and pulse current curves in a triggered and synchronized mode with the spectrum acquisition. And this we did for an aluminum application, and that's what you see here, what you get. On the two top diagrams show you the spectra from the different channels from both cathodes. And the lower diagram shows you the pulse voltage and the pulse current curves. Now, for process control, we are now picking some monitor tracks, which means that you are looking at the intensity of specific lines here. Like this was an aluminum application, so we had the aluminum line here. We are also looking at the intensity of the argon line and of the reactive gas flow. And for the pulse voltage and pulse current, we looked at the peak values, and we can also do it for the shape of the peak current or the pulse voltage. So you have several options to monitor the parameters in real time in your process. And that's what we did now in the reactive process. Of course, we started in a metallic mode, and this I mentioned already, we did in an aluminum oxide process. Here are the parameters for the process. And we started in a metallic mode. The gas flow was, reactive gas flow was controlled by the aluminum line. And we monitored simultaneously the argon line, the oxygen line, the peak current, and the pulse voltage. Starting in a pure metallic mode, we edited the reactive gas flow and made a set point to 40% of the aluminum line. And what we saw is that the peak current increased. So at this point, we did not do anything or did not control the peak current. We just monitored the peak current. And this is actually what is predicted by Shimizu in his paper. If you're adding reactive gas, the peak current will increase. If we go to a 20% set point, so adding even more reactive gas, oxygen, the peak current even increased more, and a lot of arcing was observed. If you go back to the metallic mode, of course, everything was stable and began and came back to the initial parameters and the initial settings. And now in the second step, we stabilized the peak current. We stabilized the peak current to keep the ion densities stable. And this we did in this application by changing the pulse off time of the HIPIMS pulse. So again, we started at 100% aluminum metallic mode, then went to 40% and 20% reactive gas flow for the aluminum line, and now kept the peak current stable. What we see reduced arcing, and yes, of course, with stable peak current, the pulse voltage changed. So we did apply different power at the different stages. Okay, what you see here is the peak current. Now, how does this now relate to the ion densities? And this we did in a other application, or we evaluated the data. And what you see here in these two diagrams is, again, in the upper part, you see the aluminum line at the different set points. For here, we took the ratio now for aluminum to argon, but which does not make a difference to the controlling parameter. And we went from 100% to 60 and 40 and 20% and kept this here stable. At the same time, we monitored now also the aluminum plus lines, or the ion lines, and made the ratio to the aluminum line. And what we saw here, if we do not control the peak current, the ion density were increased, or the ionization degree. Now, while we are now at the 20% reactive gas flow set point, we change now the peak current by changing the pulse off times, and we could achieve that we had, independently of these 20% set points, so it was always stable, we could play around with the ion densities or the ionization degree. And this is now kind of a playground where you can put your parameters independently of each other. In this application, ionization degree and reactive gas flow, and find out what would be the best working point for your product, and then keep it stable with an active process control. And to show that this really will work also on a long-term basis, we applied this to the same machine, but to a different application. We changed to titanium targets, and now we produce titanium oxide layer. We increased power to 6 kilowatt here to come at least close to an industrial application. And we monitored now for across both cathodes for this long-term operation. But in addition to the spectral data acquisition, we had the pulse voltage and pulse current curves here. The oxygen flow, reactive gas flow was monitored by the titanium line, parallel to the aluminum line, and now the peak current were stabilized by the charging voltage in this case. And that's what we get from doing this within 7 days. So this was a 7-day run. And you see here the titanium plus line, the titanium line, the oxygen line, and in addition, the pulse voltage and the peak current. And in the first 1.5 days, we needed to do some adjustment. We had some problems with the oxygen flow, and we needed to adjust the PID parameter. But after 1.5 days, everything was stable, and the whole process were running for the next 5.5 days without any problems, without readjustment or anything else. You see here some deviation, but these are due to putting in the carrier inside the chamber to get some layers. So that was kind of man-made. This demonstrates that active process control, in our opinion, is definitely possible and reliable in production lines, and can be used and can make the process more stable, more reliable, and increase the production yield. What I've shown you is only one part, one sensor here, which put data into your evaluation. But the overall idea, and here I'm now back to the Industry 4.0 and IoT idea, is to acquire data from different sensors, not only from smart sensors, but also from simple sensors, for system sensors, and put them all together in one database to evaluate them. What I want to stress out here, and this is very important, that you need to have some kind of standardized sensor interface to put all these data together, to have the same format, to have the same timestamp, and so on, because only with this you can apply modeling or algorithm and learn from these data and put them together in a database for maybe later on predictive maintenance. So smart sensors are important, but only one part in a big picture of this. And with this, I wanted to conclude. I hope I could show you that smart and reliable process sensors will upgrade your production. They are available today. Then they can acquire data in real time, in situ, and on a long-term basis. This will stabilize your production. This will lead to better products. And last but not least, it will increase your production lines. So we want to take advantage of the benefits of this tensor technology. That is actually one of the messages I want to give you in this talk. And with this, I want first of all thank my colleagues at the Fraunhofer IST and at PLASUS who have contributed to this work. And here are my contact details. Feel free to contact me if you have any questions or inquiries later on. And for now, I wanted to thank you for your attention. And if there are any questions for now, I will be happy to answer them. Thank you.